Hello everyone, welcome back to the next installment of Data Structures and Algorithms video series. Today we are going to talk about Kruskal Algorithm. So what is this, what are the applications of this, and how do we implement this on Java? Sit back, relax, and let's get to the video. Before talking about Kruskal algorithms, we need to have a rough idea about graphs. So, what's a graph? Graph is a non-linear data structure where data is stored in vertices and edges. So, there are vertices like this, and between those vertices, there are paths. We call them as edges. These edges can be undirected, like this, where there is no direction shows, or they can be directed like this, so whether they are showing the direction of connection. But when talking about Kruskal algorithms, we are talking mainly about undirected graphs. So they are like this, and then you need to have a little idea about connected graphs. So imagine this graph has more vertices like C and D. So if I can move from one vertex to any other selected vertex of this graph, then that graph becomes a connected graph. Right now this is not a connected graph because I can't move from the vertex A to vertex C. So if this graph was to be like this, now this is a connected graph. I can move from any selected vertex to another selected vertex of this graph. The next thing you should have an idea about is a spanning tree. So what's a spanning tree? Spanning tree is a subgraph of a graph where there is a path from one vertex to any other vertex of the graph, but no cycles are being formed. So what's a cycle? A cycle is where you started a path from one vertex, and in the end it returns to the same vertex. So here if I started from the A vertex, I can go to B, D, C, and I am returning back to A. So there is a cycle that has been formed. A spanning tree doesn't have cycles but has a path from one vertex to all other vertex in the graph. So ideally in a graph with V number of vertexes, there contains a spanning tree of V minus 1 edges. So for example, there are 4 vertices in my graph here. So 4 minus 1, which means 3. The spanning tree of this graph should be 3 edges. So if I simply delete this vertex, this edge right here, so right now I have a path from every vertex to any other vertex, but there are no cycles. So this is a spanning tree. Let's talk about weighted graphs. Weighted graphs are graphs with edges has a weight to it. So this value can be any metric value like prices or distances or temperatures, but it depends on what you are mapping. So every edge of the graph should contain a weight to it, which comes to our main function of the Kruskal algorithm, to find the minimum spanning tree. So earlier we talked about spanning trees, which means a subgraph of a graph where it has a path from every other vertex to any other vertex, but there are no cycles. And minimum spanning tree means the same spanning tree, but these using the minimum weight of the given graph. So for example, if you are considering these values as cost of something, the path that connects all the vertices together with the minimum cost is here the minimum spanning tree. And the main function of the Kruskal algorithm is to find that minimum spanning tree. Let's now see how Kruskal algorithms work with a practical example. So this is a map of an residential water supply board, and here the there are 4 houses: Mr. Kuray's house, Mr. Arachi's house, Mr. Richard's house, and Mr. Pereira's house. And the map is drawn of the water pipelines. And the metric here is given by thousands of dollars, the cost to draw the pipelines from one house to another. So now let's use the Kruskal algorithms find the minimum spanning trees, which means ultimately we need the minimum cost water pipeline system which connects all the houses with no cycle. So here the first rule of the Kruskal algorithm is to delete parallel connections and self loops. So here, as you can see, for some reason Mr. Kuray has a pipeline which comes from his house and then onto his own house. So these connections must be deleted before doing the finding the MST like this. And then again he can see from Mr. Kuray's house to Mr. Pereira's house there are 2 pipelines. One cost $80,000 and one cost $10,000. So we don't need 2 connections for the same houses. So we can simply delete this high cost pipeline like that. So now we are left with this main graph. And now let's apply the Kruskal algorithm. So the steps are to find the minimum cost edge, which means the minimum cost pipeline, this 5, which comes from Mr. Kuray's house to Mr. Richard's house. So we are selecting that, drawing that as CR, the cost of $5. 5 means $5,000. Then the next minimum cost pipeline is 7, which is from Mr. Kuray's house to Mr. Arachi's house. Arachi, and it cost $7. And then the next minimum cost edge is 8. But as you can see, if we connect 8, which runs from Mr. Arachi's house to Mr. Richard's house, if we connect these 2, there is a cycle that has been formed. So we need to ignore cycles because that is against the rules of the MSTs. So we are ignoring this and selecting our next candidate, which is 10, which runs from Mr. Kuray's house to Mr. Pereira's house. So we have Mr. Pereira here, and we have a pipeline which costs only $10,000. So as you can see now, originally we had 4 houses in our schema, and on our subgraph we have the same 4 houses, which means our MST is already being formed. So if we simply calculate the weight of or total cost of this MST, which is 5 plus 7 plus 10, which equals to 22. So rather than spending about $100,000, simply using $22,000, we can connect all those houses and without any additional cost. So that is the main use of the Kruskal algorithms. Let's see another example to get an idea. So let's go into a much complex example this time. If you are given a complex map like this, don't be afraid. If you follow the correct steps and rules, you are good to go. So the first step is to delete all self loops and parallel connections. So as you can see, there are no any self loops here, and there are no any parallel connections which connects the same 2 vertices. So we are good to go. So the next step is to find the minimum cost edges. As you can see, we have two costing edges, which is A and B and E to I. So we can add them to our MST like that, and find the next minimum cost edge, which is GH, which only cost 4. Then the next minimum cost edge is 5, which is EF. Again, no cycles has been formed, so we can simply add them to our MST. The next edges are CG and JK, which cost 6. We can simply add them to our MST. Okay, the next edge is GK, which cost 7. Still no cycles has been formed, so we can add them to our MST. Then we have 3 edges with 8. So we need to concern about the cycles. When connecting BC, no cycle has been formed, so we can add that. When connecting DH, still no cycles has been formed, so we can add that too. And when connecting FJ, still no cycles has been formed, so we can add that too. So the next cost is 9. So as you can see, if we connect CD, which costs 9, we have one cycle. So it is not approved by the MST, so we can't add that to our MST. So same here, if we connect BF, we have one cycle, so we can't add BF2. So next we have to find the next minimum value edge, which here is 12, which connects H and L. So add that to our MST, and as you can see, now there all the vertices of this graph has been connected or visited at least once, which means our MST is already here. So as you can see, with only using a few edges, we can create our MST with the minimum cost that has been consumed. So now let's go into our Java implementation and see how Kruskal algorithms is implemented in coding. Okay, so now let's go to a practical example of Java and see how Kruskal algorithms is implemented. So for this, I'm using an edge class which also has a subset class. So in this edge class is used to store edges with their source, destination and their respective weight. And there is an compare operation which is taken from the collections of Java to sort our edges. In the Kruskal example class, first we are declaring our graph using 4 vertices. As you can see, this constructor right here implements the number of vertices in our graph, and then we are adding our edges to our graph. So this graph is actually a list of edges. It's an array list. So when we are adding the edges, the first source becomes the source, destination becomes destination, and weight becomes the weight of the respective edge of our edge class right here. So basically what is happening here is this first one becomes source, this one becomes the destination, and the last one becomes the weight. So it should be something like this: 0 to 1 with 4 weight. Like that, the whole graph is being formed. The next what's happening is we are calling this Kruskal MST function, which returns us the MST. So what's happening here is we are first up we are sorting our edges from the least weight to the most weight, and then we are creating subsets which has a parent and rank. So initially all the parents going to be the vertices of themselves, and their ranks going to be 0, and then we are searching for the sources and destinations of each edges and comparing them whether they have the same parent or not, which means this function basically does the searching for the cycle function. So if x is not equal to y, which means the source is not equal to destination, which means there is no cycle here, so we simply add that into our MST and then union the source and the destination with our subsets. So here's our union function. So this recursion will happen until all of the edges are searched and search for cycles, and then finally on the result subsets the MST is formed, and we can finally print out that MST of these edges. So if we run this, as you can see, edges in our MST, we have them. So let's actually practically do this by ourselves to check this is right. So first time adding these edges, so we have 0 to 1, 0 to 2, 4, 0 to 2 with 1, then 1 to 2 with 3, 1 to t with 2, and I think I have another, yes, I have 2 to 3 with 5. So this is our graph, and then if we apply the Kruskal algorithm by ourselves, as you can see, the smallest edge is 0 to 2 with 1, and then 1 to 3 with 2, and then 1, 2, 3, 1 to 2 with 3, and as you can see, all the edges are completed, all the vertices are met, and so if we run this again, and delete this one, so as you can see, if we check here now, we have 0 to 2 with 1, and then 1 to 3 with 2, and then 1 to 2 with 3. So this is the correct MST, and that's how you implement MSTs in Java. So that is all about Kruskal algorithms in data structures and algorithms. As you can recall, it is a very effective way to find the minimum spanning trees, hence saving much as resources as possible. So I hope you guys understand the concept, and I hope you guys keep watching these videos in order to learn more about data structures and algorithms. See you in the next one. Bye.